When I was in college, it was quite frustrating to solve a differential equation. Much time has to be spent in order to solve a single equation, and sometimes the result is wrong. I also felt a lot of difficulty to understand what is going on in a differential equation. Moreover, the system could only be visualized after a lot of tedious work. All of these problems could have been solved if I had known how to use phase portrait plot. By shifting from algebra to geometry, I can stop calculating and start looking. In this video, we are going to understand the intuitive heart of the differential equation by looking at its phase portrait. Our journey starts with an underdamped mass-spring system. You can think of a variable x being passed through three blocks, each of which yields a distinct output. Those three outputs are combined into a differential equation. First, let us look at how we typically find a solution for our mass-spring equation. Here, zeta is the damping ratio, and omega n is the natural frequency. In a traditional calculus approach, we assume that the solution follows an exponential form, which leads us to a quadratic characteristic equation. The roots of this quadratic equation determine the entire personality of the system, and they depend on the balance between our mass, spring, and damper. Depending on the value of the damping ratio zeta, there are three possible scenarios. If the damping is light, we get complex roots, resulting in an underdamped system that oscillates back and forth before coming to a standstill. A heavy damping leads to zeta greater than 1. We get distinct real roots, creating an overdamped system that sluggishly creeps back to equilibrium. There is a perfect middle ground called critical damping, where zeta is equal to 1. In this case, the roots are identical and the system returns to rest as fast as possible without a single overshoot. While these formulas tell the story, the calculation is exactly what makes the process feel so tedious. And that's where we are about to pivot to a much more visual way of seeing these three realities. To make that pivoting possible, we have to convert the second-order differential equation to a system of two first-order differential equations. By denoting x1 as x and x2 as x dot, we can rewrite the differential equation in this so-called state space form. In this form, the characteristic equation comes from equating the matrix determinant to 0, which will yield the eigenvalues. This representation will be very important in deriving the phase portrait. With our state space formulation in hand, we have everything we need to draw the system's behavior. Think of this equation as the flow engine for the entire plane. At every single point, it assigns a specific vector that tells the system exactly where to go next. If we place a particle at an initial state and let it follow these arrows, it traces out a trajectory. This is a parametric curve in the phase plane. We aren't looking at x versus t. We are looking at a state moving through its own coordinate system. By plotting a representative sampling of these paths, we create the phase portrait. But why does it take a specific shape? To truly grasp how phase portrait works, we need to look at the system through three different cameras at once. On the left, we have our familiar time domain plots, position and velocity over time. On the right, we have the phase portrait, the state space view where position and velocity are plotted against each other. Notice how the oscillation is trapped between two shrinking curves, the exponential envelope. This decay is dictated by the real part of the eigenvalues, sigma. It's the force pulling the system toward rest. Meanwhile, the heartbeat or frequency of the oscillation is dictated by the imaginary part omega. In the time domain, sigma shrinks the amplitude and omega sets the pace. In the phase portrait, these two forces work together to create geometry. The imaginary part omega forces the state to rotate around the origin, while the real part sigma constantly pulls it inward. The result? The oscillations on the left become the decaying spiral on the right. The algebra of the eigenvalues isn't just a calculation, it is the geometric blueprint that determines if the traces will spiral into a rest, orbit in a circle, or fly off to infinity. The point at the center of the phase plane is called the critical point. Now, let's see what happens when we change the physics. What if we increase the damping until the system reaches critical damping condition? In this case, zeta is equal to 1. At this precise point, the math undergoes a fundamental change. The eigenvalues merge into a single repeated real negative number. Look at the phase portrait now. Instead of swinging around the origin, the state quickly returns to equilibrium without a single overshoot. The traces are generated by letting several solutions take place. The point at the center for this case has another name, the stable node. Shall we increase the damping again? Let's see what happens if we set the damping ratio greater than 1. In this case, we set it to be precisely 2. Still, there is no oscillation, but the mass needs more time to reach the equilibrium. The system has two eigenvalues distinct from each other and negative. The phase portrait is more or less similar to the critical damping case. The phase portrait is also a stable node. We still have one case left. This is the case where there is no damping at all. Definitely, the mass will oscillate forever. The phase portrait consists of concentric circles. This time, it does not spiral to the origin. The point at the center has a different name, a center. There is no decay or any energy dissipation. There are many other phase portraits that arise from different combinations of eigenvalues. Here, I'm showing you some others which I did not show earlier. Take a moment to watch them. For a more complete gallery, you should check out an MIT lecture note link in the description. Don't forget to hit that subscribe button so you will stay at the same phase as us. In case you are thinking of something, feel free to express yourself in the comment section. Thank you and see you next time.